Uh, got another lesson today regarding motion. Yesterday we talked about, well, not yesterday, the day before, we talked about Newton's laws of motion. And today we're going to continue that discussion as we talk about motion diagrams. And motion diagrams are a great way for us to represent the motion of an object. And we're going to learn how to make those today and how to interpret those. So let's go ahead. And the first thing we need to do, by the way, you should have this sheet, right? The Introduction to Motion notes, and we'll be using that throughout the lesson today. So this whole sheet is really your notes sheet in practice, and then there will be a formative with a little bit more practice for you to interpret and draw motion diagrams. All right, so back to our slides here now. To get started, it's important that we have a few definitions to understand. As we talk about motion, there's some words that we use, and we need to make sure we're on the same page with what those mean. First is a frame of reference. We won't discuss this a whole lot, but just real briefly, um, the frame of reference for motion is basically your perspective. So let me give you a little bit of a scenario here. Let's say that I am driving down the highway in a car, and there's a car in the lane next to me that's traveling the same speed. From my when I look over at that car, my frame of reference, it looks like that car's not moving. If I kind of ignore all of the surroundings that are moving around me and the noises and whatnot, if I just look at that car compared to my car, if I use my frame of reference in that car, the car next to me appears to not be moving. It has no motion because that's my frame of reference. However, if an observer standing on the side of the road was watching both cars go by, they would have a different frame of reference. And so again, we're not going to really worry too much about this. It's not something that I'm going to be asking you questions on, but it is important to know, like in physics, whenever we're trying to describe motion, our frame of reference is important. So you can jot down a quick definition for that: a coordinate system applied, coordinate plane. This is a coordinate system down here, right? So we've just applied some reference. So this is point zero, and the motion is moving in this direction, and the observer is apparently just someone standing and watching. They're not moving either. So a coordinate system applied to a situation that can be used to describe motion. Okay. All right. So now into our more important vocabulary that we're going to be using a lot today. First, there's three words: position, velocity, and acceleration, that we're going to use to describe these objects as we draw motion diagrams. Position is basically an object's location, right? It's very simple. If you're sitting at a desk right now, we could mark your position. And then if your position changes, we could mark your new position. And so any object we could say is at a certain position at a certain time. So we could define this as an object's location at a particular time relative to the frame of reference. Really, if you just say an object's location at a particular time, that's sufficient, because like I said, we're not going to be changing our frame of reference. So, okay. Um, this is starting to give us an idea of how motion diagrams are created. And so, like, if you did multiple snapshots of this biker cruising through CSU campus here, and we see, the position. Let's just take the center of the bike, or pretty close to that here. The position's at about 1 at whatever time this was taken, and then the next time interval, at the next position was about 3.5. The next position was about 6, and the next one was about 10. And so we could mark the position or define, record the position of that object for each time interval. Okay, velocity. Now, I want to mention something that's important, not as much for our class, but if you move on into, let's say, physics, okay? Speed and velocity in our class are going to be the same, or we're going to use those interchangeably. But in reality, in physics, when we define speed and velocity, they are not the same thing. Velocity is includes the change in position over a certain time. Okay, but it also includes direction. So velocity is what we call a vector quantity. And we've looked at vectors multiple times now with forces, with dipoles and bonds. And they always include magnitude. So how, the strength of the force, the strength of the pull, how fast it's going. They include magnitude and they include direction of travel. That's just a disclaimer for velocity and speed. I'm going to use those interchangeably, but just know that velocity does include direction where speed does not. And also, to put that into perspective, if a car is traveling at a constant speed as it turns a corner, the speed isn't changing because it's constant, but the velocity is changing because the direction is changing. So you can actually change the velocity of an object without changing the speed by changing the direction. Okay, so what is it? Let's define it. Speed or velocity is the distance traveled over time. So, how much the position of the object changes over a certain amount of time. In our wave equations, we used velocity, right? Meters per second, or speed, our c. That was our variable we used for the wave equation. And the units for that for speed were meters over seconds. So how fast does that wave travel? How much does the position change in meters over the time interval seconds? Okay. So we'll talk a lot about velocity here in just a minute. And then, of course, acceleration is the change in velocity. So, how much is the speed changing in a certain amount of time? And this is measured in meters per second, or meters per second squared. And again, acceleration, because it's velocity over time, and velocity is a vector quantity, its position, its magnitude and direction. If the velocity is changing, then the object is accelerating. If the direction is changing, the object is accelerating. So again, if you are speeding up and changing direction, you're changing both your magnitude and your uh, direction. Okay. All right. Also note that acceleration, in our minds, we think of, if I say acceleration, you probably think of a car like at a stoplight and it's accelerating to move forward. But in physics, acceleration can be negative also, and so that would be like the if the change in velocity is basically slowing down. That's also acceleration. That's just negative acceleration. And so please don't think that when we say acceleration, we only mean speeding up. It can also mean slowing down. That would be a good thing to write in your notes to make sure that you don't confuse acceleration as being always speeding up. Okay, so again, very important terms. Position. We're going to focus a lot on velocity and acceleration as we draw our motion diagrams. So let's move on to the next part here. And um, let's talk about how do we create a motion diagram. Okay, what are the steps of that? And I'll walk you through that. The first thing that we want to do, bring up my whiteboard here, is we want to establish a time interval that we want to record the position of an object's location. We want to record the position at a certain time interval, and it's 1 second is always a very good, simple, understandable time frame, but we don't have to use 1 second. So secondly, we want to take our object, and I'll just use my cursor here as the object. So I wish I had a little car or something I could use as a cursor, but I don't. And we're going to just pretend like that's an object. So whatever object you want there, maybe it's a person running or walking, maybe it's a car, maybe it's a dog, whatever, a skateboarder, a bike. So pick your object. Anyway, we're going to pick our starting point here, and we're gonna next we're gonna consider where's the center of our object, and then we're gonna drop a dot as that object's motion is changing. We're gonna drop a dot every time we designated for our time interval, and in this case I said 1 second, and so every 1 second we're gonna drop a dot wherever the location of that bike or skateboarder or the object is at. Okay, so if my motion was like this, okay, I'm just moving like this, right, at constant velocity, and I drop a dot every second wherever that's at, okay, it's going to look like this. So drop a dot, the next 1 second later, the object is here, 1 second later, it's here, 1 second later, and so on. Okay. So all I've done was decided that every second I'm going to see where that object is, and I'm going to put a dot at the center of the object to represent its position at that time. I'm not very good at drawing stuff, so I created actually a very simple computer program in processing to represent this motion as well, and it looks a little cleaner. And so here, what I've done is every time I click my mouse, it's gonna leave a dot. All right. And so I'm going to try to move my cursor across the screen and just kind of have like constant motion here. And let's see if I can do that. And I'll drop a dot every second. Okay, so that's kind of what a motion diagram looks like. Now you'll notice, well, with the exception of this one here, my dots are pretty evenly spaced apart. This represents constant velocity. Okay, if the change in position from here to here, I'm gonna bring my whiteboard back up. Oops, where did you go? If the change in position from one dot to another doesn't change, right, the actual distance between these, if that does not change, then we have constant velocity. I'll just use a v for velocity, and I'll use a for acceleration. All right. So we can see that the distance doesn't change between each dot, and that tells us the motion of that object has a constant velocity. Okay. Now let's go back to my program here, and let's go ahead and reset that. And now I'm going to move a little. Let's do a little faster this time. So now I'm going to try to move about like this. This is going to be a little harder to get constant motion here. Okay. I think I was relatively the same time. This is me guessing a little bit here, but look at, again, except for this one, the distance between each one of these dots is equal to each other. And so again, this is showing us that the object has constant velocity. However, compare that to the last one, right? The last one, the dots were closer together. So if we compare those two, let me come back here and we'll look at, I took a snapshot of those. If we compare those here, which object is moving faster? I guess I've got the faster one on top here, don't I? We can tell which one's moving faster by seeing how far apart the dots are. So when the dots are farther apart, if the time interval is the same, then this object here is moving faster, and this one here is moving slower because the distance between the dots is closer together. So if we go back to our worksheet, let's just look at number 3 here. Let me make this a little bigger for us. Okay. It's asking us to compare the motion between object A and B. It doesn't matter what it is. And we also have a little bit of a plane here, a measuring device, a ruler, whatever, a meter stick, and a coordinate plane. And that gives us a little bit more the ability to actually add more information to what we're doing here. So let's compare these object A and B. What do we know about them? Well, first of all, we can tell that object A is moving at a constant velocity, right? The dots are spaced equally apart throughout the motion that's represented here. So object A has constant velocity. What about object B? Object B also has constant velocity because the spacing between each dot is the same. So neither A nor B are accelerating or changing velocity. The velocity is constant for both of these. You should definitely write that down. These are kind of your examples, all right? As we go through, I'll give you some examples of each one. And then what about what's different about A and B? Obviously, their motion is different in some way because the diagrams look different. So what could we say about that? We know that A is moving faster. The position changes more than with B. And again, we're assuming that our time interval here is the same for both motion diagrams. We'll just assume that for all of them, and so don't worry about changing that. Um, we can say A, right, is moving faster than B. How do we know that? Because the distance between the dots for A is larger, and the distance between the dots for B is smaller. We can actually give more information though. How much faster is A moving? Well, it moved from 0 to 2. Okay, so it moved 2 meters in 1 second here, whereas in B, it only moved 1 meter in 1 second. So A is moving twice as fast as object B. Okay. Um, So that's all good information to write down. A lot of times you'll see motion diagrams and you won't be given the measurements for it, and that's okay. You don't need those. This is just helpful to kind of interpret the motion here. Okay. Now let's go back to my whiteboard here. And what if the position of an object is, um, sorry, the velocity is changing? And actually, I will bring up my program. Should have closed a few things here. Let's bring this up and reset it. And now what I'm going to do is start real slow, and then I'm going to increase my velocity. So I'm going to accelerate here. This is going to represent accelerated motion. But I'm going to remember I still have to click the same interval as I add my dots. I don't know how to, well, I did that, but the motion diagram looks okay. So if we look at the motion of my cursor in that scenario, look at it starts out right, the interval between the dots here is smaller, and then between here to here is a little bigger, and it gets a little bigger, a little bigger, a little bigger. So this represents accelerated motion instead of constant velocity. The object is accelerating because the spacing between in each time interval, the spacing is increasing. That tells us that the velocity is increasing. One way we can also represent that, so I'll come over here, and I didn't mention this, but let's go ahead and talk real quick. I said this is a vector quantity, and one of the things we can do, if it helps you, is actually draw arrows between the dots. And so I could just draw an arrow like this. It's kind of what we did down here, right? It's kind of the same thing as that. But this is just showing us, are the arrow length the same? Or are they different, right? So for that constant velocity from before, they were the same. And then if I come over here and I do that accelerated motion, all right, I'll just, let's see if I can erase that guy. Yeah. So dot, I'm gonna try to make it about what I did on the program there. Modeling programs are really essential. I kind of, I'd like to show you that program, let you play with it a little bit more. It's very simple, but that's a really good way for us to represent motion, is to have some kind of modeling. And this is used all the time in science, right? We just create an equation, we put it into a computer program, and then we allow the computer program to plug certain data in and see what happens. And that's basically what my program does. It's a very simple model to represent motion. And of course, we get very complex models as well. So if we look here, if I draw those arrows, right, I'm gonna have to draw this one kind of here. It's tough to draw on the screen. Um, okay, my arrows keep getting bigger, right? The distance keeps getting bigger. And so again, if that's helpful to visualize what's going on, you can see that because the distance between the dots is getting bigger and bigger, I know that this object is accelerating. And going back to what we said, we can have positive and negative acceleration. Oftentimes we'll say negative acceleration is deceleration, but in physics we don't really use that term. So you could say it has positive acceleration here because it's increasing, the velocity is increasing. Okay. So if we go back to, let's see, let's do one more scenario here. And we'll reset this. Now, let's go ahead and start out fast and slow down. So I'm going to start fast. And I'm going to start now slowing down. Okay. And again, we can tell that this is negative acceleration because our distance between our dots first is changing, right? It doesn't stay the same. So if the velocity is not constant, it is accelerating. In this case, it has negative acceleration because as the object moves, the velocity is getting smaller. The distance between the dots is progressively smaller and smaller here. So this is a good example of negative acceleration. So back here, let's apply what we just talked about to both of these scenarios. In I have object B and C here. So how could we compare these two diagrams? So what's going on with B? Well, actually, B is the same from up here, right? So B, we already know is constant velocity. So you should write that down. And if we want to add, a magnitude of that velocity, like slow or fast, maybe we would say this is slow because up here, this was faster. So just comparing those two. But then, so this is constant slow velocity. And then if we go to C here, right, what is that? What's going on with object C? And we see, just like I showed you, the dot spacing is getting farther and farther apart. So the velocity is not constant, which means we have acceleration. The velocity is changing. And is the velocity getting bigger or smaller? It's getting bigger because the distance between the dots is increasing. So we know object C is accelerating. Okay, so maybe if I said, draw a motion diagram of a car starting from a stop sign and speeding up to whatever 8 meters per second or something like that. This is what that motion diagram would look like. Okay. B would be like going through a school zone, going kind of slow through a school zone uh, when school's getting out or whatever. Okay. All right, and then we can go ahead and compare E and F here too. So E is, you can see here the spacing is far apart. Does the spacing change? Yes, it does, right? It gets smaller, smaller, smaller. And so we know that the velocity is changing. So this represents accelerated motion or acceleration. Object E is accelerating, but it has negative acceleration. And so if you want to just say it's slowing down, that's fine. We're not going to really focus on all the specific physics terms. You can just say E is decelerating or slowing down. How is that different than F? Look at F. So we've got um, distance here and distance here. Comparing those, it's definitely slowing down again. But which object slows down faster? We can see here E, right? It's slowing down pretty rapidly because it goes from 4 meters in 1 second to 2 meters in 1 second to 1 meter in 1 second. And then it's pretty much just at a slow crawl right here. This object, right, it's changed 5 meters in 1 second to 4 meters in 1 second to 1 meter in 1 second. So we can actually use that to describe the difference between these two. E slows down fairly quickly and then has constant motion for just like very slow constant motion. And F is just decelerating, it's slowing down fairly quickly as well. So again, I hope you're seeing how we can use these diagrams to really represent motion for an object. One thing I do want to point out is that I'm going to bring up our energy skate park here real quick. Bring this up. If we were going to represent the motion diagram for the skater, let's see if I can go back to this one actually. If we can represent this just going down the track, okay, this girl going down the track. Right, you notice she speeds up. She's accelerating until about here. You can see from my speed. And then she has constant velocity, right? Now, just because she started up high and went down low, we're not going to use that vertical change from high to low. We're not going to use that vertical change in our motion diagram. We're really just representing the change in velocity or position over time. So, for example, if I wanted to draw that diagram, okay, I'd see accelerated motion until about right here, and then constant speed from here. Okay, so I could draw that really quick and say, well, I know that my skater actually, let's come over to the program because it's a little cleaner here. Oops. Okay. So she is starts slow, right? And she's speeding up, and then she has constant velocity. Trying to keep those constant now. So started out slow, and maybe I should put another dot in here just to see she's starting out slower. So starting out fairly slow, right? And then picking up speed, acceleration until about here, and then she has constant velocity for the rest of the way. Notice that I didn't put my dots like in a up here and then make the ramp shape. That's not the point of the diagram. It's really just to represent the motion in a horizontal direction. So be careful as you're drawing those. Okay, let's come back here, look at a few scenarios. Um, so first scenario, chicken stands on the side of the road for a few seconds, waiting for a break for in traffic. The chicken then runs quickly across the road and then she slows to a walk to get to her coop. Now, this scenario is very unrealistic for multiple reasons, and I know this because I have chickens. Chickens don't wait for traffic; they are not smart animals, but they are entertaining. So they're kind of fun if you have chickens. All right, let's look at what that looks like. So she's standing. Let's go back to here, reset, and chicken standing here on the side of the road. Okay, waiting. Okay, position's not changing, so we're just dropping dots right on top of each other. Right now, there's a break in traffic. She's going to speed up, right, and then gets across the road and slows down and walks back to her coop. So the motion diagram might look something like this: standing still, accelerating, going fast, right? Which you can't really tell the acceleration because it's very quick, but faster speed here, and then slowing down to a walk here till she gets to her coop, sits down to lay an egg if you want to add that. All right. Good. So that's a simple motion diagram. Now, when you guys draw a motion diagram, as you're doing this, I would encourage you, like in scenario one here, I would encourage you to do something like this. So here's our initial starting point, right? Drop, um, then the motion fast, and then the motion slow. And I'd encourage you to do something like this. Okay, stopped or no motion. Then diagram this out. Okay, fast and then slow, because these are your notes. So when you come back to this, I want you to have it, so it makes sense to you. So you go, oh, okay, now I see what I did back there in case you forgot. All right. Let's go back to here. Lawn Chair Larry is actually a real scenario. If you guys are familiar at all with the Darwin Awards, you might know that natural selection from biology is where, basically survival of the fittest, right? If you don't survive in the population, you don't pass your genes on. And so for humans, we have a Darwin Award, which is just a kind of a comical way to represent stupid things people do, and they often die doing it. In this case, Lawn Chair Larry did not die, but he actually tied a whole bunch of helium balloons. I don't remember how many it was. Um, to his lawn chair, grabbed a cooler with some adult beverages, and decided to see how high he could get. And he actually got very high in the atmosphere, and moved into, I believe, if this, I think it was in California, moved into airspace for planes, and they started calling him in. And I think he got pretty scared, but he actually was able to, I think, remove some of the balloons and start to come down. But he got very high, and this was a really bad idea. So unfortunately for him, he didn't receive a Darwin Award. He got a honorable mention, since he didn't actually die and remove his genes from the gene pool. Okay, that's the whole background story to this. Check it out. Darwin Awards they're pretty funny. Some are, of course, are tragic though. So again, represents an up and down motion, but we're not going to draw in an up and down direction. We could, but if we just want to represent the motion, let's think about what's going to happen. First, he quickly rises into the atmosphere, and then he starts to slow down as he gets higher. We'll talk about why that is in our atmosphere unit, and we talk about density of the air in the atmosphere, and it gets thinner as we go up, right? So he starts to slow down, and eventually he kind of stops moving for a little bit. Then his balloons start to pop, and he quickly falls down towards the ground. So how can we represent that motion? Let's come back here. We'll use actually this again. Okay. And again, I'm not going to use the up and down. I'm just going to think about this as representing the motion from side to side here. Even though we're not representing, we are representing his motion, excuse me, in a vertical direction here, but not in a horizontal direction. So, okay, let's see. So he's set on the ground here, stopped right. He releases his tether and starts to accelerate and move quickly up in the atmosphere. Then he starts to slow down. Okay, he's decelerating here. Oops, I should have another one in there. And then he stops for a second. Okay. And then his balloons pop and he starts to move quickly towards the ground. Okay. So again, you could draw that out and then diagram. This is where he's on the ground, stopped. This is where he quickly moves upward in the atmosphere. This is where he starts to slow down because he's getting higher up in the atmosphere than when he stops. And then his balloons pop and he starts to fall back to the surface. You could diagram that out on scenario two. Okay. All right. Now, that's good practice. Scenario one and two are good practice for actually like drawing the motion diagrams. Now we want to interpret motion diagrams. I like this last scenario you guys are going to look through for a couple of reasons, but the main reason is it makes sense that if you are dripping something from a moving object, it's basically creating a motion diagram, right? If this in this scenario, this lady's car has an oil leak, so it just drips one drop at a very constant rate. And as it does that, it's representing her motion, just like a motion diagram. And you could apply this with a bucket of paint that's dripping, or somebody dropping crumbs every second as they move, or whatever. This is a good way to represent a motion diagram. So we're going to kind of look at the three different scenarios here, A, B, and C, and then we want to match them with the three different scenarios down here. So we want to see which one matches, and then we want to give some reasoning here. So go ahead and take a second. Let's pause, take a second, and I'd like you to read through each of these three scenarios. Okay, so now let's start with the first one, right? Um, Renato is driving with a slow, constant speed. She decelerated to rest, so she stopped, remained there for 30 seconds, and then drove very slowly at a constant speed. So where's our slow, constant speed here? Um, C definitely has a slow constant speed. Uh, B is a little faster. A is a little faster. We also want to look for a stop, right? She stopped for 30 seconds. And what's going to happen? We're going to drop a dot in the same spot of oil, and there's going to be a little pool of oil there, right? So one of these two, A or C, would represent that well. So we're going to eliminate B because there's no stop shown, and then drove very slowly at a constant speed. And so we see here like slow motion, stop, and even slower motion at a constant speed. No acceleration in this at all, right? So diagram C works best for this one. Write that in. And how do we describe that? Now, here's what I don't want you to do. I don't want you to describe the dots because they are already, I'm sorry, I don't want you to describe the motion that's already described here. I want you to prove the motion based on the diagram. So let's just break it down. For the first part, how do we know that she's driving at a slow, constant speed? Okay, she starts at a slow speed because the dots are the same distance apart and they're fairly close together. So that would be the first part of describing this. Then there's a bunch of dots on top of each other showing that she stopped. Then we know she moved slower because the dots at a constant velocity because the dots are close together and they're evenly spaced. So I'm using the actual, the thought process that we would go through because that's what we're thinking. What's the spacing on the dots? Are they the same? Are they different? That's the thought process we're going through. We just want to put that on paper to describe it. Okay. So again, don't just reiterate what was said here in the reasoning part because this is already stated. We want to actually talk about the spacing between the dots um, in order to describe the motion or to prove that this was the diagram that matched up with this scenario. Okay, I want you to do the same thing for these two. So pause for about 2 minutes, or I don't know if you need that long, and go ahead and do the second two. Okay, what did you get? So she rapidly decelerated from a high speed to rest and then slowly accelerated. That's going to be A because the dots here, she is going faster and the dots are getting closer together. So we can tell she's slowing down. She must have stopped because we have a lot of dots on top of each other. And for the third part of the motion, the dots are getting farther apart. So she is speeding up. And that leaves us with diagram B for the last one. She was driving at a moderate speed and slowly accelerated. So we got two parts to the motion. In diagram B, the dots are evenly spaced apart. So there's constant velocity there. And then in the next part of the motion, the dots are getting farther apart from each other. So she's accelerating. Okay. Well, I hope this helped you understand a little bit more about how we use motion diagrams to represent the motion of objects. And now I'm going to ask you to go ahead and open up the formative and complete the activities on there. There's around, I think, 10 questions, and you'll be doing some interpretation of motion diagrams and some drawing of motion diagrams. And that's it for today. Thanks.